So in this lecture we are learning about the some primary concept of vector calculus. Till now we are learning what is the scalar calculus, scalar differentiation. Here we are learning about the vector differentiation, or simply it is in another language we call it as gradient. Vector differentiations, or in another language we call it as gradient. So we have seen that when x is our scalar, then it is no problem, it is easy to differentiate it. In previous lecture we have already learned it. But if x is our vector, then it is simple lies on from what? It is a simply high dimensional spaces. If x is lie on a high dimensional space, then simply x is our vector. Then what about in these situations? Suppose let's take our x is a vector and its component, and it belongs to t-dimensional vector. Simply we denoted it rt. So its component will be x1, x2 dot up to xt. Okay, and let a constant a, it is also a vector, but it is a vector constant, and its components is a1, a2 dot up to ad. It is also a constant, it is vector constant, not a scalar constant, it is a vector constant. Okay, now the main thing is that if we multiply these two things, suppose we are considering a function that is f of x is equals to y is simply a transpose x. Means what? This is mean what? This is mean simply, if we just simply using the dot product here between two vectors, simply means here I is equals to, or lies mean 1 to d ai xi. This is mean that now here in this case, if we denoted df by dx, here x is our not a scalar, just simple, don't confuse between x, but in this case we are all taking here vectors notations. So in this case our x is a vector, not a scalar. X is a vector. So in such situations we denoted this differentiation in the vector situations we call the gradient. That is symbolically denoted del. It is symbolically denoted calling it grad or del. Okay, this symbol is called the grad, and we are differentiating for with respect to x, so of the function x. So in vector differentiation, the without using this symbol, here we are using this grad symbol. Grad or del, or grad of a with respect to x means, here we are easily understand that here our vector differentiations using our vector, here x is simple, not a scalar. Here we are using x as a vector. Okay, I think this is all about clear. Now simply if we just using this notation f of x, then what about the resultant of these differentiations? Here we are using the vector differentiation, so our resultant differentiation must be a vector. So vector is for what? Del f by of del of x1, because here if you see our x vector, they are have d component, so the differentiations will also have d components. Del f by similarly del x2 dot del f by del xt. here all the x1 are scalar. Here x1 is not a simply, here x1 is a scalar. Okay, and this thing and this total differentiation is also belongs to R times Rd. Okay, so in another language, if a functions have a more than main one variable, here if you see our functions f simple contains f is means what? Here if we using our functions f of x means what? x1 a1 x1 a2 x2 plus dot plus a dxd means here these functions f content more than one variable, here x is content more than one variable x1 x2 dot up to xd. So if for a functions have more than one variable, then this kind of differentiations we denoted this using these symbols, del f by del x1. In another language, this symbol differentiation is called the partial differentiation. Partially we differentiate these functions with respect to one variable x1. This is called the partial differentiation. Okay, don't be confused of the terminology, just try to understand what is the meaning of this symbol, what is about grad symbol or del symbol, what is about the this del symbol, capital del, small del, what is meaning about it, what's in meaning. Okay, this symbol means we are using simple single dimension symbol scalar differentiation. Here this symbol means here we are using partial differentiation. Partial differentiations mean we have for a function we have more than one variable, and here we are just differentiating this function with respect to one variable. And this del symbols means capital del, we call it in capital del in mathematics. In Greek language it called capital del. In capital del of x means we are using here vector differentiations. So vector differentiations is also the resultant of vector differentiations is also a vector. Okay, now if you just write these equations again, so our f of x is equals to what? F of x is equals to, we call it y, take x transpose a transpose x, simple summations of I is equals to 1 to d ai xi. These mean what? a1 x1 a2 x2 ADXD. Okay, yes, simple we are using d dimensions. So our del x of will be what? Will be del f by del x1, del f by del x2, del f by del xd, because our dimension of the space is d. So simple. Now what about the del f of del x1? Just write del f of del x1 means we are differentiating these f functions with respect to only x1. So if we differentiated this function, this total value with respect to only x1, then the rest of the value will be 0 and only the rest value will be this. We have to differentiate only this portion. So what will be the value? This value will be a1. Now similarly, if we write del f of del xi will be what? ai, where I is equals to 1 to up to d. Okay, so our final result will be what? A1, A2, dot, AD. So simply it is A. Here is simply here our this A. This A is not a scalar. Here it is not a scalar. Here it is a vector. It is a simply it is a vector. Okay, vectors mean it is a vector constant. It is a simple vector. Okay, don't confuse it. It is a simply a vector, and this is also belongs to our d-dimensional vector. So if you simply write this del x of A transpose x means what? A. Okay, so in vector notation, you writing this. If you similarly, if you just think this concept in scalarly, if we have this thing scalarly, if just for a minute we write this thing scalarly, d by dx or simply a j also scalar and x, then what will be our answer? Simply answer will be A. So we similarly, if vector calculus and scalar calculus both will give the same answer. In vector calculus our resultant answer will be a vector. In scalar calculus our resultant will be a scalar, but both the resultant vector will be in the same method. So it is simply in notation. Okay, now let's take an example. Suppose just remember about the logistic regression. So our loss function, if you just simply in logistic regression the L2 regularizer, okay, our loss function will be what? L of, simply our loss functions will be, just remember these equations, 1 to n log of 1 plus exponential minus yi w transpose xi. Okay, this is our logistic loss, and we are using here L2 regularizer. Our hyperparameter is lambda and w transpose w. Okay, so just to see this, here we have all the values are known, xi, yi, and lambda is also depend on how we choose the lambda, but only we have to find the w. Okay, you just write down this here. Here our known value is xi, y is other constants. It is coming from what? It is coming from our detrained dataset. It is coming forward. So yi and xi is constant, and only our unknown value is w. So this is the logistic loss function of L2 regularizer. Here unknown value is w. So simple, we know that here w is not a simply, it is not a scalar, it is a vector. It is belongs to d-dimensional space. If we have the d number of features, then this w is coming from d-dimensional space. So simply it is a vector. Okay, now if we just differentiate it, so we have to find the minimum of this. Actually, in the end of the day of a logistic functions, we have to find the optimal w, means mean of these functions. So if we find the minimum of this, we have to just differentiate it with respect to w of this L function. So what will be? So because I am habituated using the chain rule, just simply using the chain rule, you can easily find it. So what will be the chain rule? First we have to differentiate these portions. So what will be these portions? We have to differentiate with respect to w. So simply answer will be yi xi minus yi xi. Now we are coming to this portion. So what will be this portion differentiations? That is exponential of yi w transpose xi. Now we come into the logarithm portion. So what is the logarithm portions? 1 plus e exponential of minus yi, this portion. Now come to our regularizer part. It is simple what? It is our simply a L2 regularizer. So if we just differentiate it, just think about this portion. Is this, just think this portion as lambda w square. If we just see using the scalar notation, then what will be this answer? Then lambda w square, we have to just simply just think at scalarly. Then at simply using this concept, we are coming to the vector concept. So what will be 2 lambda w if we think it at scalarly. Okay. So now in vector notation, what will be this? Simply in vector notation, this will be 2 the w. Okay. Here w is a scalar, lambda is a scalar, but here is not a scalar. Simply we just using the concept, similar concept of scalar, just convert it in vector for easy of our calculation. So to find the minimum or maximum, we have to first equate the value equals to 0. Now we have to solutions, we have to find the solutions, but the main problem is that the solutions, to find the solutions of these equations is not a easy task. It's not a easy task. It is a very difficult problem. It is a very difficult problem. So in the age of modern computing, now here we are using the concept of computational technique and programmatic technique to find the minimum and maximum value. So this concept we call the gradient descent concept. We call the gradient descent. This concept is called the gradient descent concept. Means this concept is simply a computational technique concept or it is a programmatic. Okay, in the next lectures we will learn about this concept of gradient descent. Okay.